Thank you very much for coming. Thank you very much for watching, actually. I'm still getting used to giving talks at COVID times and talking to a wall, much rather looking at some faces, but of course that's not possible right now. So I'll be talking about from iterators to ranges. And well, it's about a little bit about the current standard library, but it's also about new ideas, how these ideas of ranges can be carried forward, how they can be extended for future library evolution. Now, first of all, why do we use ranges? Well, here's the old style C++ code. You have a vector, you want to sort the vector, and what you need to do is you need to pass in two iterators to the sort, the begin and the end. And let's say we sort, and then we want to erase all the duplicates. So that's, again, you write sort vec begin end, and then you write unique begin end, and that returns an iterator. And then you need to erase the elements, and you need to, again, mention end. And so you're mentioning a whole lot of vec and begin and end, and that's kind of tedious. So if we could put the begin and the end into one object, that would all be a whole lot easier. And then it would look like this. So you have a sort, and then you have the erase, and the unique, again, just takes a single object. Now, this is all C++20. And if you don't have a C++20 compiler, Eric Niebler, who is the designer of the C++20 range library, has an implementation on GitHub that also works on down-level compilers, so you can get it from there. Now, why do I think I know something about ranges? ThinkCell has been working with a range library that started back from Boost Range, and we have about 1 million lines of production code that use that library. And we have the luxury that we can evolve the library and the production code together. So we actually have one guy who's actually just doing refactoring all the time. And so he will change the production code whenever there's some new idea or some change in the library. So basically had this regular obstacle that usually exists when you have a library that is not in use and you're free to change it, but you don't really know how to change it because no one is using it. Now, when people start using it, you can't change it anymore because all the people who are using it will start complaining. We didn't have this problem because we basically could have the library and the production code evolve together. And so we could try out ideas, reject them if they didn't work, or add new ones that popped up in day-to-day business. And that way, I think we evolved quite a practical library, and we solved all these practical problems that came up. So speaking of which, if we are looking here at this piece of code, it's kind of wrong, actually. And I leave a few seconds for you to figure out what's wrong with it. Now, the problem is the sort would use the less operator, right, of the elements in the vector. Now, the unique, on the other hand, uses the equal operator. And usually these match and this will work, but if they don't, you are in trouble. And so probably, arguably, these two predicates that you're putting into the sort and into the unique, they should actually be related. And we do have a function sort unique in place that just does everything with a less operator. So the unique is no longer using the equality, but is actually saying, well, if two adjacent elements, A and B, A is not less than B, well, then these are duplicates after sorting, and then they are removed. So all you're making use of is the less operator. And of course, then you can also have an extra parameter that just plugs in a different less operator if you think that's what you need. So, and these are things that just came out in practice. There's this something where, well, we wrote the sort and the unique, and the equality didn't match the less. That probably wasn't good in the first place, but it was even worse when you're trying to use it to remove duplicates. Okay, what are ranges? Well, ranges are, first of all these containers that we know and love, vector, string, list. They all own their elements. They all have deep copying. So if you copy them, then all the elements are copied as well. And they usually have deep constness. So if the container is a const object, then you can't mutate any of the elements. And now with the range library, there is a whole different beast, which is a view. And ranges are then just these two groups together, the containers and the views. And views are different. Views are like what we are used to for pairs of iterators. And a simple view would be a subrange. And that's just that. That's just a pair of iterators. It has a begin and an end, and has a member function begin that returns the begin iterator, and end that returns the end iterator. And it references elements. It doesn't contain them. And copying would be shallow. If you copy the view, you just copy the iterators. You don't copy the elements. And it has shallow constantness, just like iterators have. So if you have a constant iterator, you can't mutate the element. If you have an iterator, you can mutate the element, but this has nothing to do with the constantness of the iterator itself. Now, the subrange that I showed you is a pretty boring view, right? So there are more interesting ones, and I will show you the two most common or most practical ranges or views that we have. First of all, if you want to find something in, say, a vector of ints, then typically you would write ranges find v4, and v is the vector. So you're finding 4s in the vector. Now, easy enough, but if you want to do the same and your ints are now stored in a bigger struct, they're just one field in the struct, then I see that's wrong. It should be a vector, not a vector of int, of course. It should be a vector of a's. And then you're trying to find that 4 in the vector of a's where the ID is 4. And you would actually not do this with find. You would do this with find if, and then write a predicate. Now you can see that these two things, these two statements do very, very similar things, but they are very different in their syntax. One uses find, and the other one uses find if, and one has an explicit predicate, and the other one doesn't. So it would be nice to be able to reformulate that in a way that becomes more similar. And now enters the transform adapter. So the transform, again, it's not a vector of ints, it's a vector of a's. And what the transform does is it turns that vector of a's into a vector of ints by applying that a transformation, a function, which in this case is just the member access for ID. And it's important to keep in mind here that this transformation actually happens lazily. So all this pipe notation here does, the views transform, is create an object that is holding a reference to the vector. And whenever, and that's it. That's the constructor doesn't do anything more. And then when you start iterating over that range, then whenever you are dereferencing an element, the transform will actually apply the transformation to pull out the ID. So the transformation is happening lazily while you're iterating. Now, if you do that, and you then get an iterator back, what is that iterator pointing to? Well, you plugged a range of integers into the ranges find. And what you're getting out is an iterator to ints. Now, what if you want the iterator to the underlying structure, to the underlying A? Well, there is a function .base that you can call on the iterator, and that gives you the base iterator back. So the iterators of that transform view support this base functionality. So you can go back to the base, to the underlying iterator. And that's all C++20. That's all standard. Now let's look at a possible implementation of the transform. The iterator of a transform, when you invoke the dereference operator, the operator star, then it needs to apply the transformation, obviously. So it needs to have access to the function. And the easiest way is just to have the function inside the iterator, stored inside the iterator. And the base can just return the underlying iterator. So in that iterator, you have a base iterator and the function. Now, let's look at another interesting adapter, a view, and that's the filter. So let's say you have, again, a range of A's, and you want the A's where ID is 4, and you want to drop all the others. So you would write it with such filter adapter. You take an A, and it returns true only for the things that it wants to keep. In this case, the ID equals 4. And again, that's lazy. You do this while iterating. So while you're basically iterating with your iterators, the use filter would take care of skipping all the elements that don't pass the predicate. Now, how could you implement such a filter iterator? So again, we have the filter view, and it has an iterator. Now, it has to carry around the function, the filter function, and it has to carry around the base iterator. Unfortunately, if you look at the increment operator ++, then it also needs the end, because when you are sitting at an element and you want to skip forward, it could very well be that you are at the last element that passes the filter. And you want to skip ahead, but you want to stop when you reached end, because you don't want to fall off the end, and you must not filter the end element, obviously. There's no element there. So you need access to the end iterator. Now, okay, let's store that as well inside the iterator. So we have two iterators, we have one function. Okay, now, how does it look like if we nest these things? Let's say we have 3 levels of filters. And obviously, if you have 3 levels of filters in one function, then you wouldn't necessarily write that as 3 filters, filter calls. You could all merge it into one predicate. But you may have that when that filter gets passed out of a function and then gets reused in another function, filtered again, and so on. So this may not be obvious that you actually have such a stacked filter in the code. And this is what the iterator would look like. So the iterator, the outermost iterator, has the function, and it stores an iterator. But that iterator again stores the function and an iterator, and it also needs to store, everyone needs to store the end iterator. And that's an iterator again that has a copy of the function and multiple iterators, 2 iterators. So you really get this exponential growth in the size of the iterator if you implement it this way. And that's a problem, right? And Boost Range actually did this. And yeah, so we found out and said, well, we need a solution here. So the idea is you really have to keep the iterators small in order for them to be passed around easily and to be, all these iterations that you're doing in tight loops to be efficient. And so the idea is this adapter object, where you pull the iterators out of, the transform object, the filter object, it actually carries around everything that is common for all the iterators, that all the iterators have the same copy of. That's the end iterator and the function. Now, the iterators themselves then just carry around a reference to the adapter object. So they reference the adapter object for all the common stuff, and they have their base iterator. So they have a pointer to the range and an iterator. Now, that's what C++20 does. That's basically C++20 state of the art. And that as a consequence has that the C++20 iterators cannot outlive their range. So that's important. You cannot just have the range go out of scope and hope to still be able to use the iterators unless this range that you have there passes this borrowed range, has that borrowed range concept, which is essentially restricted to all the ranges which don't have any internal state, that just don't store anything, and that does exist. Now, so that has a bit of a consequence. Let's look at this code, which I was actually already showing to you before, and it actually doesn't compile because the vector that gets transformed, that gets projected, where you pull the ID out of, that view object as a whole is an R value. You're creating a temporary. And C++20 says, well, if you're trying to pull iterators out of that range object, then, and this range object is an R value, then there is a danger that you actually get a dangling reference. The iterators will hold a reference to the range object, but the range object is about to go out of scope, well, because it's an R value. So the library will say, oh, well, this is dangerous. We're not going to do this, right? So in order for this to compile, you have to basically say, hey, I'm using like some library function here. You have to turn this into an L value. You have to say, oh, everything is fine. I know what I'm doing. I'm going to cast this the R value reference. I'm going to cast that to an L value reference, and then it's all good. Because here in this particular case, you don't actually have a dangling reference, because once we receive the iterator, while the range is still alive, we already call .base, and we already go back to the original iterator, and that original iterator is pointing to the vector, and the vector is still in scope. So everything is good. So sometimes you have to kind of silence these errors, or you really did something wrong. Okay, so once we have that, how does now the iterator look like? We have, again, a sequence of filters, a stack of filters. And we now it looks like this. So you have a range. You have an iterator carries a reference to the range and the underlying iterator. Now the underlying iterator again has a reference to its range. So it would be in our example, you have a reference to range 3, and then you have a reference to the range 2 that the range 3 wrapped, and so on. And well, you still get linear growth in the size of the iterator. And I mean, iterators are supposed to be really small. They're supposed to be efficient for iteration, because you're really passing them around by value, and you operate them with them in tight loops. So that's still not insanely great. You would hope you can do better. Let's see if we can do better. Now, what we are using is the index concept. It's kind of like an iterator, but the iterator, it's the operations that usually an iterator can carry out by itself, like an increment or dereference, it can only do together with its range. So you always need to supply the range and the index. And then we'll see that this actually improves matters quite a bit. And the natural place to implement these operations would be as member functions in the range. So you always pass you have a member function in the range, and you pass it an index and say, please increment that index for me. Okay. Now, of course, the whole world is not going to stop like using iterators and now all say, oh, indices are now great, and we're going to use indices instead. So that's not realistic. And internally in our code, we still use iterators. But luckily, it's pretty easy to create compatibility between these two. So if you have an iterator, say in a vector where you don't have that index concept implemented, it's pretty easy to say, oh, well, we're just going to treat this iterator as the index, because if the operation can be carried out just with the iterator, then adding the range to it is not going to break it. So that's easy. The other way around is only a little bit harder. So if you have an index and you want to make an iterator out of it, you can always say, well, I'm going to have an iterator that carries around a reference to the range plus the index. And then if you have, say, an operator plus plus, you're going to translate that into a call to the range member function together with the index, passing the index to actually carry out the actual operation. So you can pretty easily go back and forth between these two. Now let's see how then a filter looks like. Can we be more efficient? Well, a filter view with indices would look like this. The index of that filter view is really the position of where you are in your iteration. And that's the same type as the index of the underlying range. So if you're filtering a vector, the position in the vector is still the iterator of the vector. It's nothing more. That's enough. Now, and if you increment, you would kindly ask your base range to increment the index. You say, hey, vector, you can increment indices, right? Your index, it's the iterator, so that's easy. And you can also tell me what your end iterator is in this case. So you can just ask the base for these things. And then you can write it pretty easily. You can say, okay, it's just increment the index until you hit the end, or if you pass the filter, then I'll also need to return. I need to stop incrementing. So that's efficient. And the key thing here really is that the index type of the filter is the same as the index type of the underlying range. And that means when we now create an iterator for this filter, then we actually, our iterator is still just basically two machine words. It's the pointer to the range and the index. And that index doesn't grow in size, no matter how large the stack is of filters that you stack on top of each other. Okay. Now, there's one more peculiarity with C++20 ranges, where we maybe can go beyond what C++ ranges provide. Now, if the adapter input, the input to a filter or transform, is an L value, then the filter, the C++20 range filter or transform, they create a view. And that view is a reference to the has reference semantics. So when you copy it, it's O of 1. It doesn't copy the elements, has shallow constants, and so on. So this is what you see here. You create a vector and you filter it. Okay. Now, what happens when you create a vector in place as an R value and then want to filter it? Well, with current C++20, this does not compile because, as I said, these adapters contain references to the underlying range. Now, if the underlying range is an R value and will go out of scope any moment, then it's gonna have a dangling reference, and that's a problem. You may say, well, okay, why not then just always have the vector declared outside of that filter, so have it as a separate variable, and then I can easily reference it. Well, the problem is you need to keep these two things in scope, and they need to be able to reference each other. Let's say you have a function where you want to return a lazily filtered container. So you have a container, and it's already there. Someone produced it. And now you want to say, okay, I'm only going to I want to pick certain elements of that container. And some of my users may not even need the whole container. Maybe they only need the first element. So it would be awfully nice if I could just return a lazily filtered container. The memory is going to stay there. The vector still has memory allocated, but as soon as you kind of throw it away, as you say, okay, I just got my first element, I'm done with it, I'm just going to throw all the memory away. But there's no real reason to do anything more with that memory. I don't need to run through that memory and filter it all if all I need is the first element. Well, that's hard to do with C++20. So one attempt would be you create the vector and then you make a tuple and try to return both the vector and the filter. But the thing is, you get a dangling reference because what you passed into the view filter, the vector there, is of course no longer in scope. You returned a tuple with a vector, but this filter is not pointing to the vector in the tuple. It's pointing to the vector that is a local variable in your function. So that's a problem. So for C++20, I don't think there's a good solution. We said at ThinkCell, we said, well, if the adapter input is an L value, we just do what C++20 does. It's just a view. But if it's an R value container, we need to take care that this R value container stays alive. So in this case, we actually create a container where the filter aggregates that underlying range. So it makes a copy, it copies it into itself, and creates a different kind of object, a kind of a container object that would have deep copy, deep constants if what you copied is a container. But it's still always lazy. And what's important here, I think, is that I think laziness and containerness are really orthogonal concepts. One is you're carrying out around all your elements, okay, but it still may be useful to be able to iterate lazily and to do lazy transformations on that container, because you may not need to do all these transformations on all the elements. Some few elements may just be enough. That's all you need. So I think you want to have these two things to be orthogonal. There's another trick we can play. The find, of course, will always does what the find does. It returns, it iterates through the range. If it finds it, it returns the iterator, and otherwise it returns end. For people who do C++, that may seem terribly natural, but maybe we can make that a little bit more flexible and easier to use. Now, let's say we have a customization point that tells us what to do when you found something and what to do when you didn't find anything. Okay, and then the regular customization would be, well, if I found something, then I just return the iterator. And if I didn't find anything, I return end. Okay, so that's the natural thing that you would do. But now you can fold into this customization point, and that's something actually we took from Boost that didn't carry over to C++20, but liked it. That's in Boost range, they have that kind of customization. You can do something like return element. You can say, I don't want to return the element or end, but I only want to return the element. And in code, you quite frequently probably have, okay, I find something, and then I have an assert that the iterator that you got is not end. Well, this is exactly that, but it's much more terse, and it's also much more expressive. So you basically just say, okay, just give me an element. I'm not expecting an end here. Now, what you can also do is you can return the element, or if we are supposed to return end, we wrap the iterator into something that has an explicit operator bool, that is bool evaluatable, so that you can do an if directly on the iterator. So it's kind of like a null pointer. With pointers, we have this all the time. We set a pointer to null, and we don't need to compare that null pointer to the end of any container. The null pointer stands by itself. It's just null, and it's not pointing to anything. And it would be nice to have that for iterators as well. And this is what we have here. Unfortunately, we still have to attach a little boolean. It's effectively like an optional iterator, except for the special case when you have pointers. Then it's okay. Pointer is an iterator, so for that special case, you can use just the null pointer. It would be nice to be able to use a value initialized, like default value initialized iterator, but it's currently not allowed to compare arbitrary iterators. You can only compare iterators if they really belong to the same range. And so you need to currently, with the current standard, you need to attach a little bool. But it's still very practical. It's very expressive, very easy. You don't have all these end checks in the program. All right, let's go one step further. Now, so far we talked about ranges with iterators, and it may seem very natural, but you may have cases like this one where you say, okay, you traverse something. You traverse a data structure, like you traverse widgets, and the list of widgets that you are actually traversing is not in any container in a linear way, but it's some sort of structured thing where you have to walk through and enumerate your elements. And I think we write these kind of things all the time. These enumeration functions, these for eaches. And it's kind of like a range, right? But it doesn't have iterators. Now, it would still be nice to be able to treat it like a range, to use the regular range algorithms on it, so that you can have like the commonality in the code. You can have the same kind of canon that you name kinds of words, expressions that you use. So here you could run an any-off, and this lambda here that just is traversing widgets would be a range. And you can just stick it into the first parameter of the any-off and then have your predicate here. Now, how can we do that? First of all, what are we actually doing here? C++ iterators do what's called external iteration. So you have the consumer sitting at the bottom of the stack, and it calls into the producer when it wants an element. So every time you call *it, you call a function, you call up the stack, and that generates the object that you want, or a reference to it, and it returns it to you. And so that's the consumer is at the bottom of the stack, and the producer is at the top of the stack. Now, being at the bottom of the stack is great, because you have a contiguous code path for your whole range. You can consume your whole range in one go in the program. So that makes it easier to write things at the bottom of the stack. And you get better performance because all your state is encoded in the instruction pointer. So you don't have to you're not called and you sit there and say, well, what's my state? Where do I have to continue my program? You know where you have to continue your program, well, where your program is currently running. So that's pretty easy. And you can also use the stack as much as you want for memory. Now, if you're sitting at the producer, at the top of the stack as the producer, you only have a contiguous code path for each item. So the operator star of an iterator is called each and every time you want an item. And it's always the same call that's being made. And you have to figure out, if you have a complicated data structure that you want to iterate over, you need to figure out, okay, where am I in that data structure and how am I going to continue with my iteration? That makes these things harder to write, and they also have worse performance, because every time at the single entry point, you basically have to possibly branch, and you have to say, I have to make a dynamic decision, how am I going to continue the iteration? And for the time of your iteration, you also have a fixed amount of memory, because it's essentially anything that you can store inside the iterator. Or you have to go to the heap, but then you have to allocate heap memory for your iterator, which is probably not what you want. Now, we can turn the whole thing around. We can say the producer could also be at the bottom of the stack. And then it has all the advantages of being at the bottom of the stack. And the consumer is at the top of the stack. And as I said, we write these things all the time. So we write a function that's called for each something. And then we call it and plug in a lambda, and that lambda is then being called for each and every item that you're enumerating. So if you're saying, well, the producer or being at the bottom of the stack is great, and being at the top of the stack is not so great, then can't be both at the bottom of the stack. That would be the ideal world, right? Well, they kind of can with coroutines. Now, coroutines are basically two separate threads, separate threads of execution that pass control over from one to the other. One said, okay, I'm going to consume an item, and the other guy is continuing running its thread until it created an item, and then it passes it back to the other guy to consume, and then he's doing some consumption, and then he's going back again and say, okay, keep producing items. So your control flow is basically jumping back and forth, and that is supported. There are basically two flavors how to implement this. One is stackful. That means essentially you really have two, not threads, but at least operating system fibers, with real stacks that are running in parallel, kind of, and passing control one to the other. It's like cooperative multitasking. The problem is they are quite expensive to set up. They need 1 megabyte of memory just for the stack, for example, virtual memory. And switching between them is not something that actually the compiler understands. So it's not very efficient. There is an alternative, which is the stackless coroutine, and they are now coming in C++20. They're great. The problem with them is that the whole call stack basically has to be a coroutine. So when you are producing these widgets, then your whole way of producing these widgets, every time you do a subroutine call in particular, if you do a function call, that function has to be a coroutine as well. It doesn't seem to be so bad here, right? Your traverse widgets is a coroutine, and then it will call into this function here as a coroutine as well. That's fine. But if you say something, well, like I want to iterate, I want to use algorithms in my code that are not necessarily aware that I'm doing anything here with coroutines, then it doesn't become so easy, because the for each is not a coroutine, obviously, and you don't want to replicate maybe the whole standard library to be coroutines. That's one thing. Then and otherwise, if you don't have coroutines, you can only yield in a topmost function, which is somewhat restrictive, which you can overcome by calling into coroutines, which we showed. Now, it's still a bit expensive to do coroutines, because every time at the resume point, when you're resuming the coroutine, it's still kind of like a dynamic jump. You still need to decide, okay, where am I going to continue, and you still need to save and restore some registers, and so the compiler will have more trouble doing aggressive inlining with coroutines. So basically merging these two threads together into one. And be really as efficient as if it would be all one function. Now, in addition, internal iteration is often good enough. We often don't want anything else. So if you're running something like a find or a binary search, obviously you need iterator. But if you're looking at for each, accumulate, all of, any of, none of, all these don't need iterators. They are basically the for each is the quintessential. I only want to get called for each and every item. Well, that's what internal iteration provides. You don't need external iteration. In addition, the adapters actually also get by with internal iteration. But in particular, filter and transform can be implemented, no problem, with internal iteration. So the idea is we want to support ranges that support only internal iteration. So we will call now things not only with iterators a range, but we'll also say, okay, if you give me something that supports internal iteration, I'll accept that as a range as well. Let's see how any-of, for example, is implemented in that case. So you have the function any-of, it stores a result, and then it for each is over the range. And the for each is really the common interface. That's the common way to access a range, irrespective of whether that's external iteration or internal iteration. The for each is kind of always works. It does what it's supposed to do, and in this case, it passes you all the contents of your range, and then it decides whether to set the internal variable to true or false, and to endorse it with what you've already accumulated. Now, it seems like that's okay, but if I'm writing okay question mark, then it's probably not okay. Okay, I have to go and do your questions. I will get back to your questions. Maybe let me break real quick because I have questions. So okay, I'll ask. There's Peter's question. Let me take a short break for questions. So how does find lambda compare with find transform performance-wise? Shouldn't make any difference. It will inline it. It's nothing. It's okay. Does now 29 does it have a superfluous type def? It has, okay, I don't see the type def on 29. Why don't you want to return a std optional on slide 40? Yes. That's a good question. Why don't we return a std optional? Because that's not what we want. Not what we want. That's not the syntax we want. The std optional would be you would access the iterator. You want to access the iterator with star it. That's your value. That's what when you're dereferencing the iterator. Now, if you were to return an optional, it would be star it, which is kind of weird. That's not what you want. So the thing is, if you check if it, then you're just checking the Boolean operator. But star it is your dereferenced operator. If it's your dereferenced iterator. Okay, so that's the distinction there. But internally, they are effectively the same, unless we make progress with the standard and we allow some sort of null state for an iterator that we can actually check for, which shouldn't be too hard because, I mean, they are internally pointers, and that's something we should be able to do. Okay, let me see. Now I have to find back, right? So any-of. Right, so that's not okay. Why is it not okay, our any-of implementation? Because any-of would actually stop when true is encountered. When there is a true, then any-of stops. So what's missing here is the ability to stop our generators. So we have a generator, enumerating all the elements, and we're saying, okay, like, hold on, just stop. I'm done. You know, shut up. I want to finish now. How do you do this? Well, the first idea was it's great. We just throw an exception, right? And then it's good. It stops. You're going to throw out of the generator. Well, good. Of course, it doesn't work because it's way too slow. Now, second idea is we return a special type from the enumeration function. And based on it, we decide whether to continue or not. So here it's like basically, okay, if as soon as my result fell over to be positive, then I actually would want to break. I want to break out of the for each. And And that's nice, because you can actually find out at compile time whether one of these enumerations that these sinks that you call, whether they actually return that special type, break or continue. And if it doesn't return that special type, you know this thing is never going to break. And then you can just at compile time elide the whole check. So that makes it more efficient. We don't want to have branches again, right? Now, you would think, well, okay, you have these sinks and these generator ranges, but maybe they're not terribly frequent, and our iterators were just good enough. Well, turns out these generator ranges can be helpful even in the context of things that can be implemented with iterators, like a concat. A concat is not C++20, doesn't have concat yet, like concatenation of several ranges, but it's certainly doable. It's practical, and actually range v3. Eric Niebler's library does have it, so expect it in the standard soon. Now, if you look at how concat is implemented, inside the concat range, you have, again, references to two ranges. And you have, and whenever you say references to two ranges, this may be a copy in case it's an R value, but I'm just going to ignore that here for simplicity. So you have references to two ranges, and the index of that concat range is a variant of the two indices of the two ranges, right? So you can either be in range 1, and then you have an index of range 1, or you can be in range 2, and then you have an index of range 2. Now, every time you want to increment that index, you now have to make a choice. Either you have index 1, and then you have to increment index 1. And once you reach the end of range 1 with index 1, then you have to switch over to the beginning of range 2. Or you already are in range 2, and then you can just increment. That means we have branches for each increment, which is not terribly nice. So how to, and here's the reference, it's the same thing. So when you dereference the iterator, there's again going to be a branch, because you need to know, do I have index 1 or do I have index 2? And I need to branch on that. So how do we avoid all these branches? Well, I mean, with generator ranges, it becomes so simple. You just have an enumeration function. That enumeration function will just call for each on these two ranges in sequence. And then you're done. Oh, good. So the thing to take away here is that iterator-based ranges are actually even for iterator-based ranges, sometimes the generator interface is actually higher performing than the iterator one. And then if you only need a generator, then you want to pick the generator. If I only need a for each over a concat, this implementation is always better than the one that uses the iterators. And then you want to use that implementation. And you can make that choice automatically in the library, so that you don't have to, the user is completely oblivious. I'm not gonna know. Okay, the same actually is true for filter, because there, when you are deciding on whether to pass a particular value or not, then you need to generate that value. Now, you may be filtering something like a transform where dereferencing is expensive. So if you filter, then while you're iterating, while you find your next element to return, you need to basically do the transformation for all you have to generate the values of the things that you're filtering. And then you return, it's like, okay, now I'm at the right position. And then the dereferencing comes, and you have to again do the transformation. So you do the transformation potentially twice in a filter. And you can again avoid this with a generator, because there you just get the value and you look at the value and say, well, is that good or not? If it's good, then you just pass it on, and otherwise you just ignore it. So it's every value is only generated once. Okay, now there's also, of course, std format in the C++20 library, which is a new way to format text, which is certainly vastly better than what we had before. I was a little bit disappointed that it is not so much married to the range library. And actually, it can be done, because if you look at how the formatters are written in the std format, so std format, usually you can give it doubles and ints and stuff like that. That's all you supported out of the box. But if you want to do specific things, you can actually define your own formatters, and the underlying interface for these formatters is using output iterators. So you will receive a call with an output iterator, and you say, well, anything that you are when you're now formatting your value, please write all your text for that value. Please write this into this output iterator, and you're just going to feed the output iterator. Now, output iterators are really internal iteration. You call the output iterator if you have a value. So it kind of fits nicely into this fold of generators. So here's an example. You have, say, a double, and you write something like a concat. You concatenate simply the text that you want to write before, U1, and then the number of dollars, again, as some sort of description of how you want this thing to be formatted. Again, here it's 2 decimal digits. And then you just have this thing as a single range, as a single concatenated range. And when you just write it like this, it doesn't get evaluated, right? It's more like an expression tree. You generate it's just an object, and only when you start iterating over this object, then it would actually do work. And I think it's nice to have a single unifying concept for text formatting and for the ranges we use elsewhere in the program. Now, keep in mind, this is not like IO stream, right? So in IO streams, you could just put the double somewhere in the middle and it would just format the double. And that's not the idea here, because the double itself is not really a character range. It's a single double. So here we are really talking ranges. This TCS DEC is nothing magic. It's just as much of a range as your literal is. It's a range. It's text effectively. So this is also easily extensible. You can say, well, if I'm frequently printing dollars and I want to prefix it with a $sign, and then I want to have always 2 decimal digits, you just write a little function that returns that range and that incorporates the double, and then you can use it anywhere in your texts. Okay, another thing we probably want is placeholders, right? So if you want to say, well, it's curly braces 0, this is where I'm going to put I want to format my thing into, my number into, and that's also pretty, I think pretty unifying, because this TC placeholders is not going to be terribly smart. It doesn't do any formatting itself. All it really does is it takes a literal, typically, or string, and it does replacement, and it replaces these placeholders with, again, ranges. These things are not, they're just text. Think of them as text, and this text just gets replaced in here, and that's all this thing is really doing. It's a bit like Lego. You just plug it together, and it works. And every individual function is pretty simple. Now, okay, we also have support for named arguments. That's fine. That's not too hard. One difference you probably saw here between std format and this library here is that the formatting parameters, like for example 2 decimal digits, are not part of the format string. I would call this a feature rather than a bug, even if people like Python don't do it, and that's why probably also std format didn't do it this way. But when you're doing internationalization, the translator usually needs the power to change around placeholders, because some languages may have things in a different order. And then he needs to move things around, maybe swap things. But usually what you don't want the translator to do is influence how things are printed. I mean, if you're printing dollars, you're always going to print it with 2 decimal digits. And even if you have to change the comma into a dot as a decimal separator, that's probably something you're going to pull out of some OS library, where you say, okay, for this language, and I know my language, that's the best decimal separator to use. And I don't have to. This is not something that the translator has to control for every single point, every single place where the number is being printed. Okay, now to finish this up, we're going to talk a little bit about how we then get these things into containers, because when we format things, we have to get them eventually into something, some string, for example. And so far it was all just concat, and we built these big, objects which are describing strings, but at some point we want to flatten them into a string. So how do we do this efficiently or conveniently as well? Now, the string already gives us an empty construction. So an empty string is this, right? Now, you can construct a string also from another literal or another string. That also works in C++ already just fine. Now, it's probably pretty uncontroversial that you want to also construct a string from a single range. I know that there are plans in the standard to do this range to, say, vector conversion to allow that. And so in the best of all worlds, I think you would be able to plug a single range in here. And here's another one. But if we already have the string that without any parameters is empty, and with one parameter, it's that one parameter. Well, why don't we say, well, with two parameters, it's just the two parameters concatenated. And then we made it variadic, and we just can pass any number of ranges, and they all get concatenated together into the string. So this would look like this. Essentially, you're just omitting the TC concat. You could achieve the same with if you wrote TC concat. You may say, well, but in this great world, what do we do about the existing constructors of string that take multiple parameters? Well, let's look at them. So the first one takes 3 elements out of this buffer. This buffer doesn't have 3 elements, so that's undefined behavior. This constructor here, you can briefly think about what it does. It actually adds 65 times a Control-C to your string, which is also less than intuitive, I would say. Now, the last one finally does what we really want. It adds 3 times an A. Now, I would say, let's deprecate this stuff. We should actually write it like this. We first have an abstract way to say, okay, I want 3 times this A. And it's not something that depends on being a string or anything. You can use it with a vector. It's just, again, a range that you're creating. Maybe you don't even need to instantiate that. Maybe you can use it lazily in a way that you can just iterate over it. And range v3 does have a repeat n. So these things would be, in my opinion, should be written like this. Now, of course, we can't just change around the standard library, right? So standard library is what it is. So we invented a little explicit cast to kind of introduce all these constructors that we think should be there but aren't there. So there you can write all these things when you use the library. Right, I think I'm seeing the discussion. Repeat n could be constant evaluated returning the character. Yes, it could be. Yes, it could return. And I'm not sure whether you would need that though, whether you actually want a, here Peter says you can say, you can have the repeat n, constant, like evaluated at constant time. Well, I'm not sure that's even efficient, because then you would need to copy the whole block of memory, which may not be very efficient. It probably is easier to say, if at the end I want to have basically allocated on the heap potentially something like a string, then it's probably better to say, okay, I'm just have to fill it with 10 times the A, for example, rather than having the block of A's in memory and just copying it over. It's all different, of course, if you can have const expr strings, and then these const expr strings, then they are lying in memory, and that's probably good. Anyway, so now in top of the explicit cast for the strings, there is also an mplace back wrapped just to use the explicit cast. So you have a vector, and you want to mplace back something that is a string to it, and that's then possible. So the std string, this thing will automatically convert to the std string. Would be nice. TC append works. We also have that. So that's for appending stuff, where you again can use it variadically, very similar to the constructor. Now, what I want to talk about here at the end is, how do we get this formatting to be fast? Because in text formatting, one argument is often has to be fast. The complaint with IO streams were, oh my God, these are painfully slow, and so that's bad. So we have context for strings. Okay, if we have context for strings, then super. Then we can generate repeat n10 at compile time. The fast formatting into containers. So how do we do this efficiently? I think the most efficient way to do this would be you determine the string length first, then you allocate the memory for the whole string at once, and then you just fill in the characters. That's probably the most efficient way to do it. Now, how can we get there? So one first attempt would be, we say, okay, we have an explicit cast that is filling containers, that's creating containers. We're just going to iterate over the range and just have the two iterators being passed in the container, like we did it before. Now, the problem here is, and I was kind of surprised that that's the case, for non-random access ranges, if the range is that you pass is non-random access, the string constructor or the vector constructor will actually run twice over the range because it will think it's very important to determine the length up front. So it will run first over it once to determine the length, and then it will run over it again to copy the characters. This is probably fine as long as we didn't have ranges, because the things that, running over something like a list, it doesn't do arbitrarily much work. It's certainly not terribly fast. If it's a list, it's kind of scatter access to memory, but still, I mean, it's still bounded. Now with ranges, this is different. And we've actually been bitten by that, because if you're writing very complicated ranges with transforms, with filters, and the filters need the values that come out of the transforms, then iterating over a range is suddenly quite expensive, and it can very easily be the dominating factor in filling the container. So then this I'm just going to iterate over it to find the size is not really a good way to do it. I'm just going to look at range. Yes, this is the explicit cast. Ranges begin is certainly constrained, and this is just, yeah. Peter's asking whether the ranges begin is constrained, and then explicit cast range should be constrained. Yes, this is just a sketch. You can't write it like that. But the idea basically stays. You're just passing the two iterators to the container. Okay, so yes, so maybe we don't want to run over the whole range before we actually allocate the memory. Maybe it's sometimes better to just say, okay, I'm just going to allocate the memory, and I think the decision there was also made because copying was expensive. So just allocating the string or a little part of the string, or say the vector, and then generating elements, and then reallocating would mean copying all these elements. Now in C++, prior to C++ 11, this was very expensive, but now we have moved and it become a whole lot more efficient. So I think and at the same time, as I said, with ranges, it's now potentially expensive to generate the elements. So the trade-off that's made here, it just changed over time. So maybe we can do something like this. We can say, okay, if our range somehow finds out about the size, it has some internal ways to do it, then we're just going to use that. We're just going to have a container, we reserve the size that we need, and then we iterate over the range and place the individual elements. And we can't use insert because that would again start iterating over the range. So that would be one way to potentially improve performance. Now for append, we can do it in a similar way. There is a little tricky problem here. And if you take a look at append, or if you take a look at this for a moment, maybe you can see it. The evil part is the reserve. Reserve is evil. I think reserve is misdesigned. The thing is, with reserve, it will just allocate as much memory as you need. The thing is, if you're calling append with small ranges repeatedly, then this reserve will just increment the size of the vector, or whatever you're creating here, just one element potentially at a time, and would cause massive amounts of reallocation. And so I think we first need a better reserve. Reserve is broken. So let's write a better reserve. So let's say, okay, if we have a reserve and the capacity is not enough, then make sure that the capacity, the current capacity, is increased by a fixed factor, and at least. So that even if you are inserting things one by one, then things you don't get these crazy reallocations. And we use that reserve everywhere because I figure that the excess memory that's being reserved is outweighed by that safety, that even if I call this in a funky call pattern, then I don't get these massive reallocations. Okay, now we have this. So with cont reserve. So all I talked about here is iterators, right? And that's not, well, that's not really enough. We need our generators. So what do we do about the generators? Now, there is a customization point we can add to produce appenders for containers. So basically sinks that know how to add things to containers. And that's this here. And they are being obtained from the container. And for standard containers, they just it's a sink, right? So it gets called here with individual elements. It doesn't break, right? So it returns a void, and it just doesn't end place back. Now, maybe it sounds a little bit overdone because, I mean, this is really just a back inserter, right? So this is just basically an output iterator where you pass in the elements. Well, we need a little bit more, because what about the reserve? Doing the reserve is kind of critical. And the sink needs access to the whole range to ask it, hey, do you have a size? Can I somehow prepare for what's happening now? And so the way we thought about doing this is that there is on these sinks in general, and this doesn't only apply to appenders. This is just for anything that you pass into this for each, and anything that is a sink for your container. For your range that you are iterating over. All these things may contain a chunk member function, and that chunk member function is enabled if the sink is interested in looking at the whole range or pieces of it while iterating. So it doesn't have to be the whole range. For example, when you do a concat, you're iterating, say, over 3 ranges. Each of these 3 ranges is invoked via a separate for each. And maybe for some of them, the sink wants to do something special. So and then it would enable that chunk overload, or the chunk member function, and then would get the range. So what in this case, if the range has a size, then I know I can reserve before. So I'm just going to do the reserve here. And then I just forward to the regular for each. So I'm just going to, this basically casts away my appenderness I derived from the appender container. So my reserveness. So I'm no longer reserving. I'm just going back to what I would originally do. Okay, you cannot only use this for appenders. You can also, for example, do it for files when you're writing to files, because the files can advertise that they're actually interested in contiguous ranges. I want something that's contiguous, and if it's contiguous, I can use just a single fwrite to write it to disk. Otherwise, I would have to call individual writes, which is a whole lot slower. So you can use that to speed up writing into files. Now, question is, with all that, how much loss do we have compared to real handwritten code? How much faster are we going to be? Or how much slower are we going to be? So here's the straw man, the handwritten repeat 10 times A, 10 times B, 10 times C, writing this into a container. And the container, again, is something that is very, very simple. It's just a fixed buffer. We don't care about buffer overflows. We just this is basically just raw speed. We are just writing stuff into buffers. And that's the straw man. That's the simple way to do it. The raw, close to the metal way to do it. Now that's the straw man. This is how we actually want to do it. So we want to say, well, we append to your buffer, and we are writing this concatenation of a string to it. So that's pretty high level. You're using this repeat end function, and you're just passing it 3 different ones of them so that they're all being concatenated. And the appender to the buffer is going to be, again, very simple. It's just going to write stuff to the end of the buffer and increment the buffer end. So what are we losing? Basically, this over that. And it turns out, well, not a whole lot. So if the repeat n is actually iterator based, we lose about 50%. So it's 50% slower, more time. Now, if the repeat n has internal iteration, which is it can easily have, then we are only about 15% slower than this close to the metal. I'm just going to dump everything into memory. And here, this is really the worst case because the actual formatting is essentially not doing anything. If you, instead of a repeat n, you would format a double, for example, then formatting this double would actually involve real work. And then this overhead of writing things into a buffer would be even smaller. So we are getting very, very close to the basically fastest possible way to actually format text. Now, we could do a little bit better if we just write, if we want to write into basic strings. So here, I created a little toy basic string implementation. It's essentially just allocating on the heap. And you have this, again, this trivial formatting task of formatting these 10A, 10B, and then 10C. The point here is the standard appender is somewhat inefficient. The problem is here, when you are emplacing into a container, the container always has to check, am I at the end and do I have to reallocate? Now, well, that's something that you don't really want to do all the time because we already determined with our reserve that we've done it. We're already done with it. So potentially a more knowledgeable low-level appender for a string could say, okay, if I already allocated the memory, I know that I have enough room. I can just blast the bytes into there and don't have to check for any end. So it would kind of look like this. So your for each is no longer using the cont emplace back. Instead, it's just basically writing memory. And the string was only 30 characters long. And we actually included here the heap allocation. So we actually went to the heap, allocated the memory, and still the custom appender actually saved 20%, which is not bad. Of course, this requires us to rewrite the basic string. So we'd have to have our own basic string implementation, which we currently don't, because the uninitialized buffer is not exposed by the standard containers. All right. Now there is a bit of future work. So if there are special cases when, for example, the size can't be found for all the snippets that you want to add, maybe there could be a new customization point that says, okay, if my range, maybe my range knows not the exact size, but maybe it can tell me a minimum size, and then the minimum size could always be 0 if you don't know anything. But if you know some things, like in the concat, where you say, okay, I have a bunch of literals here, I know how long they are, but I don't know how long, say, the expansion of the number is going to be. So in that case, you could just say, okay, I'm just going to add up all the length of the literals and already allocate. When I put this into a string, I already know how much to allocate in advance. And maybe I have to reallocate once, but no more than that. Same or similar situation when you have a file. Often you have fixed I/O buffers. You have a buffer, and you have like maybe 500 bytes to go. And it would be interesting to know: is there a chance I'm going to overrun these 500 bytes? And if you would support something like a maximum size, then you could say, okay, my buffer still has 500 bytes available. I can just write into that buffer without any check, and I'm more efficient that way. All right, and then there was Peter at the end. How does TC format compare with the format library? Well, we don't really have. There's no real TC format, right? It's just ranges, and we still use it for formatting. And I haven't used std format. I think std format is fine, and it certainly was used for compatibility with Python, or designed to be compatible with Python, so people know how to use it. I like doing it range based, in particular because it makes this customization terribly more easy. So when you are quite frequently, we have these concats that are putting together these expression trees, really, or these not yet evaluated strings, and we pass them out of functions a lot. So they are you are when you want to print a website, when you want to print an HTML page, you may have different blocks of HTML, and you want to compose them. And it's suddenly becoming very easy to just do this by putting together these lazy parts, these lazily evaluated ranges, and to compose them instead of generating a string eagerly each and every time, and then copy the string again, and copy the string again, and copy the string again. This way, you just basically just build this whole tree of objects, where only the things that are actually, the data that is actually is held only by reference, possibly, and so the whole thing is very compact, and then it gets all just blown up into a string in one single go. So that's very easy doing it this way. It would be quite hard to do this with std format. It just doesn't, one std format doesn't so easily plug into another std format. You have to go and make a string in order to do that. All right. So conclusion: ranges are very useful, and I showed you the index-based ranges and the generators to improve the performance a little bit over the C++20 iterator-based ranges. And there are also ways to unify ranges with text formatting. Now we have all this range stuff, and our library is on GitHub. Here it is. You can take a look at it. I want to say I hate the range-based for loop. It has been introduced quite recently, but it just makes people write this instead of that. Thank you very much. And if there are any more questions, go ahead. To propose TC ranges for standardization, do we have any plans for standardization? Well, I must say not really. The problem with, we like to change stuff all the time. And I think the library is as good as it is because we could change stuff. And I feel there's still, even after we've, after so many years passed, there's still things which we change. The treatment of UTF, Unicode characters, or they're just, always something that we change, and that we could we make it a standard proposal? Yeah, maybe it's also a lot of work that it would require to make it a standard proposal, and a lot of politics that are inevitable if you're in such an international environment as the standard committee. So probably this will stay ThinkCell, but maybe some of the ideas can be, maybe someone else will pick it up, and the standard, the future development of the standard library is going to be a little bit influenced by what we do.